let's go ahead and move on to our last panelist now from this, or last speaker now from this session, Gary Barnhard. Gary, if you're there, looks like you're here. You can come off mute, come on camera, and share your slides if you will.
Okay, so you want me to share them?
Sure.
Okay, we'll just go through and.
And one second before we start, Gary.
Okay.
We are going to push the panel back by half an hour to give everybody a nice break after your talk, Gary.
Okay.
So there'll be a break right after this. And so the panel on challenges and critical steps to advanced power beaming will begin at 2:45. And that time we're going to take out of the breakout session. So the breakouts were going to be up to an hour and a half. We'll make them be about an hour. So go ahead, Gary. That's
okay. Great. All right. I'm Gary Barnhard. I'm the president and CEO of Extraordinary Innovative Space Partnerships, Inc. It's a company that's been focused on cislunar mission development activities. This presentation is put together by myself and Dr. Seth Potter, senior consultant with LSIC, Inc. And what we'll be addressing is power and ancillary services beaming, reducing the systems engineering to practice. Next slide, please. This is basically gives you a visual mosaic of what we see as the challenges of space power and ancillary services beaming, starting off with a whole range of ground testing activities through to space test beds, technology demonstration activities, both in the space-to-space environment, ranging from technology development to demonstration to deployment, and then on to other venues, including surface to surface, surface to the moon and asteroids, and in time space to Earth. This is actually a very high resolution slide that can be dived in on in detail. And there's also two posters that we have in the sessions, one of which includes this. Next slide. Okay, this is a challenge. Well, it's defined as a challenge matrix that we prepared actually, from a request from AFRL. And the idea is this attempts to lay out the relationship between TRL advancement in terms of the progression in technology development to demonstration and deployment as a mission. It's sort of like the old, to paraphrase Lewis Carroll, via the Cheshire Cat. If you have a good idea of where it is that you're trying to go, it sure helps make it easier to get there. So there's really two work vectors here: the TRL advancement, as well as the alternate venues, as indicated, and there's a difference in terms of the relative value of delivered power. And the idea here with a challenge matrix is if you're trying to accomplish something, can you basically lay out a path that says, if I put my resources here, I can stack the deck towards success, or bias it that way towards that end. And we're in this particular case, we're focusing on the intersection of how we can take the space-to-space mission development efforts that we've been tilting at and relate them to the surface-to-surface problems in the lunar applications. Next slide, please. We started off with our space solar power beaming mission overview. Basically what we were looking to do was unbundle or disaggregate spacecraft electrical power systems, providing beam power and ancillary services as utility. We wanted to support the further development of power beaming technology. We wanted to try and make progress with respect to this notion of TDQ missions to bridge the technology development valley of death. We wanted to have a TDQ mission which defined a civilian non-weapons use of space solar power. We wanted to address real and perceived cost, schedule, and technical risks associated with the use of space solar power and ancillary services beaming. Again, something that could build on the access to multiple venues and their different fundamental figures of merit. And the goal would be that to use the beamed energy to support sustained ISS co-orbiting fleet flyer operations, enhanced power requirements and augmented propulsion, loosely coupled modular architectures, and potential new cluster architectures. Next slide, please. This gives you a visual overview of what we had proposed, starting out with a transmitter on space station that would have some level of, would be robotically compatible and some level of gimbaling capabilities, reaching out to a 6U CubeSat that would be co-orbiting for some period of time with the station. Next slide, please. This is one of the interesting notions that it's illustrated here, is that if you go off and do this, how are you going to go through and have anybody except for the engineers pay attention to it? And the idea that you could go through and incorporate a visual representation of what was actually happening with respect to beam impingement, seemed to be an interesting cross between theater and in a good representation of being able to show people what you're doing. Next slide, please. In terms of critical considerations, we view space power and ancillary services infrastructure as both an applied engineering problem and an economics problem. Applied engineering, because the solutions are valued in terms of availability, durability, resilience, and maintainability, not as new science or engineering. Economics, because the solutions are necessarily sustainable utilities that will circumscribe what is possible. And as a consequence, each application and venue has these challenges to face, and different fundamental figures of merit and or value propositions associated with the same. In operational capabilities, as other speakers have indicated in yesterday, are best realized by leveraging a combination of technology development push and mission requirements pull. Next slide, please. I identified the work vectors in that challenge diagram. We really do need to be able to accommodate both the technology evolution and the understanding the relationship and the ability to leverage work in different venues. Furthermore, we think that each increment of the public and or private investment should lead to an operational capability, useful and used by one or more missions. Funding technology sandboxes is not going to necessarily get us where we need to go. The efficacy of any systems architecture must consider the entire life cycle of the field equipment with respect to cost analysis, functionality, scalability, durability, and maintainability. Engineering solutions which leverage other, you kick the slide, please. Engineering solutions which leverage other mission investments should be given priority but not exclusivity. And furthermore, approaches should be based to organically grow the community of interest so that they become increasingly invested in the success of the endeavors. Next slide. We went through and, in cooperation with a lot of our colleagues, have been iterating, what constitute the key variables and how to lay them out. This is, getting to be a fairly consistent set in those regards, and it maps very well into, for example, what Dr. Jaffe has presented, and others. We need to be able to characterize things. What we're okay, you can proceed to the next slide. This is what we've euphemistically referred to as the money chart, because many folks had jumped down our throat as to what's the real value with respect to power beaming, particularly when you're dealing in the millimeter or microwave regions. And so what we went off and did is we looked at 3 different cases: the low end of Ka band, where the achievable power density for the particular parameters that we were working on for the space-to-space power beaming mission were significantly lower than the solar constant. Kick it up to the high end of Ka band, you're now on the order of double the solar constant in some configurations, where you can start thinking about at least demonstrating something of some utility there. If you manage to kick it up into well into W band, we looked at the 95 gigahertz case. You're more than an order of magnitude more than the solar constant. You're talking about actually being able to deliver something of real value in terms of utility. Next slide, please. This is filling in a little bit more detail on what we were looking for the space station transceiver. It's actually, this shows is a three-axis gimbal approach with multiple robotic interfaces, which show up. Go to the next slide, please. This is designed so that it could be accommodated on both the Barto facility, Bartolino more aptly, as shown here. And next slide, please. And also on the gem exposed facility. The idea being is that there are more targets of opportunity near term with Barto, but there's lower power available with the gem exposed facility. There's potentially higher power available, but it's the idea that you could go through and incorporate both robotically compatible interfaces. Seemed to be an interesting evolution. Next slide, please. Then since the issue of solving co-orbiting issues with respect to space station became somewhat problematic, we went through and examined the idea that you could go and transition the 6U CubeSat into a robotically compatible attachment that could be added to a space station logistics carrier that after a primary delivery was taken care of, it could be attached to the logistics carrier. The logistics carrier outfitted with some number of co-orbiting experiments. It would then co-orbit with the station for some period of time and use the robotically compatible power and ancillary services beaming apparatus to support both meeting additional power requirements for experiments, as well as high-speed communications and data relay back to the station. Next slide, please. What we're looking for in terms of applications and customers here was, really to use space beaming applications, including expansion of mission operation capabilities, power densities in order of magnitude above the solar constant, multiplex power and ancillary services, including comm, data, navigation time, leading to enhanced situational awareness, enhanced spacecraft and infrastructure design and flexibility, outbound orbital trajectory, insertion, propulsion, and pave the way for what we euphemistically call the Lunar Power and Light Company. The government space applications fall under sustainable, interoperable, high power generation, storage and distribution, frequency agnostic extension of the cognitive software defined radios, and operational flexibility and situational awareness leads to an enhanced space power, all triple entendre intended. Next slide, please. As we mentioned, the idea of repurposing the pressurized logistics carriers as crew-tended co-orbiting labs is something that is extant and actually is emerging also in terms of different commercial lab initiatives, supporting other crew-tended space manufacturing elements. Looks like it's going to be a business to be in. And laying out what constitutes a true cislunar utility needs to be laid out across all the different orbits and venues. Next slide, please. In terms of the technological challenges, as we've heard from a large number of speakers in these discussions. The physics of at least near field and far field energy propagation are pretty well understood. It's not new physics. Okay, the use of radiant energy to transfer power, data, force, and or heat, either directly or by inducing near field effects at a distance, are not well understood. Moreover, there's very limited engineering knowledge base of practical applications. Accordingly, this is applied engineering work, aka technology development, not new physics. And to optimize the beaming applications, we need to better understand how each of the components of radiant energy can be made to interact in a controlled manner. Next slide. And those consist of both electrical components, magnetic, linear and angular momentum, thermal, and data. And their potential direct and indirect uses for each of the beam components. And use of any combination of these components has implications for all of the spacecraft systems. Next slide. In theory, the use of the component interactions can enable individual knowledge of position and orientation, shared knowledge and loose coupling, the interfaces between related objects, near network control, fixed and or potentially rotating planar beam projections, and the potential for net velocity along any specified vector. An interesting quote that I think is germane here is, in theory, there is no difference between theory and practice, but in practice there is. Next slide, please. In terms of the additional challenges, as we found, in terms of the economics, mapping the financing to terrestrial power and ancillary services utility analog, it just happens to be in space, seems to be meeting with some promise. In each, we have to cope with the fact that each addressable market has different fundamental figures of merit. With respect to public and private partnerships, finding out how to draw out the confluence of interest that actually can support substantive agreements has been a challenge that we've been working with our mission development consortium. And geopolitical, basically we need to make international cooperation and collaboration real on this. Next slide. This basically is a timeline that came out of the ULA sponsored CIS Lunar efforts. And the key thing here is to stress the point that there's this whole series of iterative and recursive milestones. Okay, this is a process that we have to orchestrate the engagement in. Next slide. This is a example of that we did between the XISB and consortium, including Raytheon, where we went through and defined a Eclipse Lander payload concept that could provide a credible level of power and ancillary services beaming services, literally taking equipment that's been built, repainting it and putting new decals on it. It is absolutely not optimized for space use or for the intended application. However, what we found was that we could deliver something that was real and useful, and particularly for things that would be within 100 meters of the landed craft. And the closer that you can get, you could provide a real operational capability. So our argument here is that let's go and do something real with the tech, find out how we can actually support customers and make something happen. And this this particular approach to demonstrating this by orchestrating both the distance input power and receive power seemed to be an interesting and compelling way of laying that out. Next slide, please. This is stretching into a broader visualization, co-opting a collection of NASA images with novel augments. But the idea is that there's some distance, as we go through, and build a microgrid environment that orchestrates all these pieces. There's going to be some combination of power conduits that are required, whether or not they're wired, wireless, and the interoperability between the different systems that's going to make for a viable microgrid. Next slide, please. In terms of next steps, the Space Solar Power and Ancillary Services beaming mission is a XISP Inc. commercial TDQ mission moving forward with the advice and consent of NASA HEOMD. It is strictly commercially and self-funded at this point. Requests for allocation of ISS National Lab resources, commercial cargo space, ISS integration support, mission development investment have been submitted. NASA may participate indirectly through the ISS National Lab and or other direct means. ISS intergovernmental agreements, SpaceX agreement funding, and or other to add or move forward additional milestones. In parallel, to provide an assured path to execution, the direct commercial purchase of services agreement is being worked consistent with the enacted NASA ISS commercialization policy. Additional partners, participants, and customers are being sought across the commercial, academic, nonprofit, and government sectors. Opportunities for international cooperation leveraging the ISS intergovernmental agreements are being developed, and the balance of funding, cash and in kind, will be raised from the SSPB Consortium investments and XISP Inc. debt equity financing. Next slide. Conclusion, the space-to-space power and ancillary services beaming has transitioned from a conceptual mission pregnant with opportunity to a commercial mission with recognized standing. There's now a defined confluence of interests biased towards successful execution of the mission as a public-private partnership. Successful demonstration of space solar power beaming will, we hope, reduce the perceived cost, schedule, and technical risk of space solar power in general, and pave the way for the use of space solar power in multiple venues, including space-to-space, surface-to-surface, surface-to-lunar, and infrastructure services and space to Earth. Online is Don't Wait for the Future. Help us make it. Next slide. And what's next? We thank the Lunar Power and Light Company. Thank you all very much for the opportunity to present.
Great, thank you, Gary. And one thing that I think this is nice is you're really focused on the pragmatic ways that we can actually put this into practice, and that's exactly what our panel discussion is going to be coming up next. So,
and if you go through and check out the posters that we included in the session, there's not only the high resolution version of the challenge visualization, but also a more even more pragmatic engineering dive into the details of reducing the systems engineering to practice. And there's a whole range of papers and presentations that we have on the mission development work. Thank you all.
Yeah, great, thank you. So now everyone, we'll reconvene at 2:45 for our panel on critical challenges and critical steps to advance our power beaming to get this into practice. See everyone back at 2:45.